Welcome to our lecture video in fluid mechanics with the topic Fundamentals of Fluid Flow. In this video, we will answer the sample problems number 1 to 4 in the handout. And this is our first problem. A pipe carrying oil with specific gravity 0.85 changes in size from 150 mm at section A and 450 mm at section at B. A is 3.6 meters below B and the pressures are 90 kilopascal and 60 kilopascal respectively. If the discharge Q is 150 liter per second, determine letter A, the head loss, and letter B, the direction of flow. So we have the pipe changing from diameter 150 millimeters to 450 millimeters. So, and the pipe A is located 3.6 meters below B. So we will start the smaller pipe here at the lower portion. So with the diameter of smaller diameter of 150, and it grows in size. Is the bigger diameter. So this is 150 mm diameter pipe, and this is 450 mm diameter pipe. This is point A and this is point B. And the distance from the vertical distance is 3.6 meter. And given also is the pressures from A. We have here 90 kilopascal. And for B, we have there 60 kilopascal. Given also the discharge as 150. So given the discharge Q equals 150 liter per second. So we will convert that into cubic meter per second. So that will be multiplied with. Every 1 cubic meter we have 1,000 liters. That is equal to 0.15 cubic meter per second. So we will need to find the head loss and the direction of flow. So having this figure from A to B, so our energy at A is equal to the energy at B plus the head loss. So there is our head loss. So this is our equation 1. And here, our EA so our EA here is BA, or velocity A squared, all over 2G plus PA over gamma of the liquid. And what liquid it is? Oil. So we have our liquid as oil with specific gravity 0.85 plus the elevation head. Okay, is equal to, for energy at B, so we have their velocity head, so V squared over 2G plus the pressure head over gamma of oil plus the elevation head plus head loss. So we need to find the values for V velocity, we can get that by using the formula for Q, which is Q is equal to, so Q is equal to area times velocity, Q abel. So therefore, we also need to remember that since this is a singular series flow, so the flow of water is series. Therefore, we can have the value of QA equal to QB. And that is equal to 0.15 cubic meter per second. So Q ABA, so Q is equal to AB. 0.15 equals the area at pipe A, so that is 150 mm. So pi over 4, 0.15 squared times BA. Therefore, we have the value for BA as 0.15 times 4 over shift pi times 0.15 squared. So 8.49 meter per second. So VA is 8.49 meter per second. For VB, QAB, and then VB. So we have Q as 0.15 equal to pi over 4. And then for diameter at B, that's 450 mm. So 0.45 squared. And then VB. We can now have the value for VB as it's not 15 over there, 0.94. So 0.94 meter per second. So let's substitute it. Since there's already values for pressure given, we also have the elevation of ZB as 3.6. Then we were able to solve for the values of VA and VB for VA and VB. So we can now substitute it. So this is our equation 1. So we can now substitute them, those values. Substitute in equation 1. So VA is 8.49 squared all over 2 times 9.81 plus PA is 90. And our liquid is oil with specific gravity 0.85 times 9.81 plus our elevation there is 0 equals our velocity head for B is 0.94 squared over 2 times 9.81 plus 60 kilopascal over 0.85 times 9.81 plus the elevation 3.6 plus the head loss, which is what we are looking for. So what is now the value for head loss? Head loss is 8.49 squared over 2 times 9.81 plus 90 over 0.85 times 9.81 minus 0.94 squared over 2 times 9.81 minus 60 over 0.85 times 9.81 minus 3.6. So we have here 3.63 for the head loss. So 3.63 meters. That is the head loss. So that's for letter A. And letter B, what is the direction of flow? So for the direction of flow, we need to get the value for EA and EB. So what is the value for EA? The energy at A is equal to, for B. For B, we have EA. So EA is 8.49 squared, 2 times 9.81, plus 90 over 0.85 times 9.81. So 14.47. Whereas EB is equal to 0.94 squared, 2 times 9.81, plus 60 over 0.85 times 9.81, plus 3.6, and that is 10.84. 10.84 meters. So since EA is greater than EB, therefore fluid flows from A to B. So that's the answer for number 1. Let's go to sample problem number 2. A pump takes water from a 200 millimeters suction pipe and delivers it to a 150 millimeters discharge pipe in which the velocity is 2.40 meter per second. At A, in the suction pipe, the pressure is negative 40 kilopascal, and at B, it is 400 kilopascal. B, discharge pipe, is 2.4 meters above A. What horsepower would have to be applied by the pump if there is no losses? Okay, so no head loss. So the drawing is not given, but we need to understand that from the description in the problem, the point B here is 2.4 meters above A. So B is at the top, and given also the diameters 200 mm for the suction pipe, which is at A, and then 150 for B. So we're using here pump. So we're using a pump. So that is the drawing for number 2. So this is our suction pump, and this is pump, and then suction pipe, and then this is our discharge pipe. So what are we looking for here? What horsepower would have to be applied by the pump if there is no losses? Question mark. So we're looking for power. So P is question mark. And the head loss here says that it's equal to 0. So therefore, if we're looking for the power, and then we're using pump here, EA plus head added is equal to energy at B plus head loss. But since head loss is 0, we can cancel like that. So VA squared, so velocity head, plus pressure head. So we're using water. So our liquid is water. Plus elevation head, plus energy added equals velocity head at B plus pressure head at B plus elevation at B, and no head loss. So this is our equation 1. And since this is another series flow, so we can say that QA is equal to QB, and that is equal to AB. So area at B equals velocity at B. So given the velocity at B, so here (2.4 meter per second) at the discharge pipe, at the 150 mm discharge pipe. Therefore, we can get the value for Q. So 150 mm diameter and 2.4 meter per second. So our value for Q now here, so this is Q. Oops. Shift pi over 4 times 0.15 squared times 2.4. So that is 0.042 cubic meter per second. 0.042 cubic meter per second. Then we can now get the value for, since we have Q now here, we can now get the value for VA at A. So that is equal to 0.42 equals pi over 4 of what's the diameter at suction pipe? That is 200 mm. 0.2 squared. And then we're looking for velocity at A. So VA is equal to 0.042 times 4 all over shift pi times 2.2 squared. So 1.34. That is 1.34 meter per second. Then, given the pressures, so given the pressures at the suction pipe of negative 40 kilopascal, and then at the discharge pipe as 400 kilopascal, we can now substitute all values at equation 1. Substitute in equation 1. So our VA is 1.34 squared all over 2 times gravitational acceleration, plus the negative 40 kilopascal, and then we're using the liquid water, 9.81, plus what's the elevation at A. So we're going to use this as a datum line. So this is our datum line, meaning this is our elevation 0. So our elevation for A is 0 plus energy added equals velocity at B. That is, where's the velocity at B there? 2.4 squared over 2 times gravity plus the what's the pressure, that is 400 kilopascal. So 400 kilopascal over 9.81 plus the elevation of B, that is 2.4 meters. So 2.4. So what's now the value of HA? Head added is equal to 2.4 squared over 2 times 9.81 plus 400 over 9.81 plus 2.4 minus 1.34 squared 2 times 9.81 plus 40 over 9.81. So that is HA now is 47.45. Is 47.45 meters. And then we will use this HA for the formula power is equal to Q gamma E. So this is our formula for power. So Q, gamma, E. Wherein our E here, our E, this is different color. Our E here is the energy added or the energy extracted. So depending whether you're using pump or turbine or motor. Okay, so power is equal to, our Q is 0.042. Our gamma is water. Let's use 9810 kilonewton, 9810 Newton per meter. So it is in Newton. Then energy is 47.45. So the answer here will be 0.042 times 9810 times 47.45. 19,550,349. So 19,550.349. And this is in watts. And we will convert this in horsepower because in the problem, it asks the power in horsepower. So take note that 1 horsepower is equal to 746 watts. So we will multiply this with 1 horsepower over 746 watts. Cancel watts there. So power now is equal to 19,550.349 divided by 746. So the answer here is 26.21 HP. So this is a power in horsepower. And this is output, this means that it is the output power for pump. So this is example number 2. Let's now go to example number 3. Water enters a motor. So this time we're going to use motor. So water enters a motor through a 600 millimeters diameter pipe under a pressure of 14 kilopascal. It leaves through a 900 millimeters diameter exhaust pipe of a pressure of 4 kilopascal. The vertical distance from the center of the two pipes is 5 meters. If 500 liters of water pass the motor each second, determine the, letter A, power supply of motor in kilowatts, neglecting any loss. B, if the motor is 80% efficient, what is the head acting on the turbine? So, there's no drawing. Again, from the description, we are using motor. And the vertical distance from the center of the two pipes is 5 meters. Sorry, it's 5 meters. And we have here the exhaust pipe. So, exhaust pipe, that is 900 mm. Then water enters into a motor. So the drawing here is like this. We're using motor here. So the distance, vertical distance is 5 meters. So motor, we're going to use the motor here, or sometimes turbines, motor or turbine. So when we're using turbines, we're going to do the similar solution as we do with motors. So here, when we're dealing with motors or turbine, our equation is energy at 1 is equal to the energy at 2 plus the head extracted or the energy extracted. So head extracted, HE. So for E1, we have here the velocity head, V1 squared over 2G, plus the pressure head, P1 over gamma. So what are we going to use here? We're using fluid water. Then we have the elevation head at 1 equal to velocity head at 2, pressure head at 2, plus the elevation head at 2, plus the head extracted. So, given the value for Q, 500 liters, so we can now put here Q is equal to 500 liters. That's supposed to be 500 liters passing the motor each second. So, each second, so that is definitely the Q. Multiplied with 1 cubic meter in every 1,000 liter. So this is equal to 0.5 cubic meter per second. So since this is a series flow, Q1 is equal to Q2 is equal to A1B1 is equal to A2B2. So since we have Q as 0.5, so we have here 0.5 is equal to pi over 4. What's the diameter for area 1? So that is, the pipe 1 is 600, the pipe 2 is 900. So this is 0.6 squared, then velocity 1 equals pi over 4, and this is 0.9 squared, and then V2. We can now get the values for V1 and V2. So V1 first. Our V1 is 0.5 times 4 all over shift pi times 0.6 squared. 1.768. So 1.768 meter per second. While V2 is 0.9. 0.786 meter per second. So 0.786 meter per second. So since we have now our velocity, we have our pressure, given the pressure 14 kilopascal for the 600 mm pipe, and then 4 kilopascal for the 900 mm pipe. Then we have also the elevation for 1 is 5 meters, and then the elevation for 2 is 0, since we're going to use this as datum. So this is our elevation 0. So we now have to substitute it in equation 1. Substitute in equation 1. So V1 is 1.76. So 1.768 squared all over twice of gravity plus the 14 kilopascal, then water, plus 5 meters elevation equals 0.786 squared over 2G for pipe number 2, plus the 4 kilopascal pressure head, and then plus 0 elevation plus energy extracted. Therefore, we can now have energy extracted here as 1.768 squared, 2 times 9.81 plus 14 over 9.81 plus 5 minus 0.786 squared over 2 times 9.81 minus 4 over 9.81, that is equal to 6.147. So energy extracted is 6.147 meters. So, the question, power supply for letter A. Power supply of motor in kilowatt, neglecting any loss. So, no loss, no head loss. For letter A, we will use again the formula power is equal to Q gamma E. Now, this time, our E here is the head extracted. So, our Q is 0.5, then water 9810, and then our E is 6.147. So power, not yet. Is it in watts? In kilowatt. Okay, in kilowatt hour. In kilowatt, sorry. So 0.5 times 9810 times 6.147. That is 30,151. So 30,151.035, and that is in watts. So the power here is 30.15 kilowatts. So that's for letter A. And this power here is the input power for motor or turbine. For letter B, what's being asked? If motor is 80% efficient, what is the head acting on the turbine? So it's asking for the head acting on the turbine. For letter B, we have here the formula efficiency is equal to the power output divided by the power input. And this is the formula for efficiency. So since we have our power input for the motor, so we have the efficiency 0.8, that is 80%. So we are looking for the power output. So it says there, what is the head acting on the turbine if the motor is 80% efficient? So power input is 30.15. So power output is equal to 0.8 times 30.15, 24.12 kilowatt. So 24.12 kilowatt. And then from the formula, P is equal to Q gamma E. So 24, so this is our power output now. 24.12 is equal to 0.5 times 9810. So since we're using kilowatt here, kilo, so look at what happens here. This becomes 9.81 in kilonewton per cubic meter times the E. And this E here is the HE. So what is our E? (24.12) divided by 0.5 times 9.81. So 4.92 meters. So that's the, it's asking for the, what is the head acting on the turbine. So that's for number 3. So let's go now to the last example. So for the last example in this video, we have a pump shown. So this is our pump here. It draws water at reservoir A with elevation 20 meters and lifts it to reservoir B. So water is lifted from reservoir A to reservoir B with elevation 70. The loss head from A to point 1, so this is our point 1, is 2 times the velocity head in the 200 mm diameter pipe. So this is our 200 mm diameter pipe. And the loss of head from point 2 to B is 10 times the velocity head in the 150 mm diameter pipe when the discharge is 0.03 cubic meter per second. Determine, letter A, output horsepower of the pump. And then letter B, the pressure heads at 1 and 2. And for letter C, if the pump is 75% efficient, determine the head added by the water drawn from A. So head added, we're looking for HA. So since we're talking about pump, obviously we are looking for the head added. So let's go to letter A first. What is being asked again in letter A? So the output horsepower of the pump. So we're going to need to solve for the output horsepower. So what are we going to do here now is the equation here is energy A plus the head added, since we're talking about pump, equal to EB plus the head loss. So there is a head loss from point A to B. So we have here the velocity head over 2G, which is, there is no velocity head since the point A is exposed. So point A is exposed, so we're going to remove the velocity head for A plus the pressure head here. Since it is again exposed, the point A is exposed, therefore we're going to remove the pressure head. As long as it's exposed, the point being in question is exposed, which is our point A at elevation. So it's given at elevation here. And here for the B, they are all exposed to the atmosphere. So there is no velocity head and there is no pressure head there. Now as for the elevation, so there is elevation there, it's given. So elevation for A, the water at A. So plus head added equals, as for B, point B, there is no velocity head for point B since again it's also exposed. There is no pressure head at B since it's also exposed. And there is elevation for B. Then we have here each loss, head loss. Since we're going to deal with the separation of pipe, so we will divide this pipe into two, this portion here and this portion here. So we're going to divide the head loss as well. So I'm going to put here head loss from A to 1 plus head loss from 2 to B. But if you add this head loss here, the total answer is the head loss from A to B. So what's left here is the elevation head plus the head added equals the elevation head of B plus the head loss from A to 1 plus the head loss from 2 to B. And this is our equation 1. So since we're going to deal with the separate pipes, so here we're going to deal here separately. There's going to be another formula for the point A to point 1. Oh, the condition. So there is a condition here that the loss head, so here the loss head from A to point 1, it's talking about this, the loss head at point A to point 1 is 2 times the velocity head in the 200 mm pipe. So how do we show that? The head loss, so it says there, the head loss from A to 1 is equal to, it says there, 2 times the velocity head in the 200 mm diameter pipe. So 2 times the velocity head of the VA over 2G, or VB, V1, I should say V1. V1 over 2G. But we need to find what's the value for V1. So we need to find the value for V1 by the discharge. So from the discharge, let's just direct that one. So from the discharge Q, our discharge here is 0.03 cubic meter per second. 0.03 cubic meter per second given. So A1 V1 is equal to A2 V2. So 0.03 equals pi over 4 times the diameter is 0.2 squared V1 is equal to pi over 4, diameter is 0.15 squared V2. So we can now have the value for V1 and V2. So 0.03 times 4 all over shift pi times 0.2 squared, that is 0.955. 0.955 meter per second. Whereas V2 is equal to 1.698. 1.698 meter per second. So we can now have the head loss from A to 1. So twice of V1 is 0.955 squared all over 2 times 9.81. So head loss now here from A to 1 is 0.955 squared all over 2 times 9.81. So 0.093 meter. Now how about the head loss at 2 to B? The loss of head from, so the loss head from point 2 to B is 10 times the velocity head in the 150 mm diameter pipe. So 10 times the velocity head in the 150 mm diameter pipe, head loss 2 to B is 10 times the velocity head in 2. So this is 10 times our V2 here is 1.698 squared all over 2 times 9.81, and that is equal to 10 times 1.698. So 1.469, or say 1.47 meter. So that's the head loss 2 to B. Then from our equation 1 here, so substitute to 1. ZA, our elevation at A is 20. So 20, and then for B it's 70. So 20 plus the head added equals 70 for the elevation at B, plus head loss A to 1 is 0.093 plus head loss from 2 to B is 1.47. So what is our head added? So that is 70 plus 0.093 plus 1.47 minus 20. So 51.563 meters. 51.563 meters for head added. Therefore, we can now have our power Q gamma E, and having E here as the head added. So Q is 0.03. Our liquid is water, 9.9810. And this is 51.563. So the answer here is in watts. 0.03 times 9810 times 51.563. So 15,174.991. So 15,174.991 watts. And we have here 1 horsepower is 746 watts. So cancel watts there. So we have 15174.991 divided by 746, and that is 20.34 horsepower. So power is 20.34 HP. And this is output power for pump. Now what's the question for B? The pressure heads at 1 and 2. So we will cut here to reveal the pressures. We will cut these portions here. So we will draw that for letter B. For letter B, let's redraw the part here. So this is our water. So our water is at elevation 20 meters, 0.8. And then this our 0.1 is at elevation 0. So this is the cut portion. So our equation here is EA is equal to energy 1 plus the head loss from A to 1. Obviously, there's no pump here or turbine, so we just have this equation here. So since the A here is exposed in the atmosphere, therefore, we will cancel the velocity head and the pressure head. So as long as the point is exposed in the atmosphere, there is no velocity or pressure head there, and also it's stagnant here. As you can see, it's from the reservoir, so it's stagnant there. So this is ZA. There's elevation head. For the pipe, obviously we have velocity head, and then we have pressure head because it's contained, it's inside. And then we have Z1, that will be 0 because the elevation there is 0, plus what's our head loss from A to 1? Head loss from A to 1 is 0.093. So given as 0.093. So elevation head is 20 equals the B1. We were able to get the value for B1, was our B1 a while ago, there, 0.955. So 0.955 squared all over 2 times 9.81 plus the missing pressure head plus the elevation Z1 is 0 plus 0.093, the head loss. So P1 over gamma, or the head loss at pipe 1 is now equal to, that is 20 minus 0.955 squared all over 2 times 9.81 minus 0.093. So 19.86. So 19.86, and the unit here is meters. So that is the pressure head. It's asking for the pressure head. Now how about the pressure head at 2? So we will cut it here. And we will consider only this portion. Then we will draw that portion here. So this is our pipe. Our reservoir. Then this is our pipe number 2, pipe at 2.2, and the elevation here is 0, and the elevation of B is 70. There. So the equation here is energy at 2 is equal to energy at B plus head loss from 2 to B, and we have value for head loss to B already. So since this is enclosed, the point 2 is enclosed, so we can have velocity head there. We also have pressure head on pipe 2 because it is enclosed. And then the elevation here is 0, equal to the pressure head, and the velocity head at the reservoir is 0. So velocity head and the pressure head at reservoir B is 0, but it has elevation head and the value for head loss to B. Head loss to B there, it's 1.47. So 1.47. So V2, what's the value for our V2? Once again, our V2 is 1.698. So 1.698. 1.698 squared all over 2 times 9.81 plus the pressure head plus Z is 0 equals our ZB. Elevation B is 70 plus 1.47. Therefore, our pressure head now is equal to 70 plus 1.47 minus 1.698 squared over 2 times 9.81. So 71.32. 71.32 meters. So that's the pressure head at 2.2. So that's for letter B. Now what's letter C? It's asking for if the pump is 75% efficient, determine the head added by the water drawn from A. So determine the head added drawn from A. So knowing that we have already the power output here, so we're going to compute for the power input. So says there, head added by the water drawn from A. So this is letter C. We're looking for PI. So again, efficiency is equal to PO over PI, power input over power output over power input, 75%. And then our power output is 15.17. Then our PI is 15.17 all over 0.75. So 20.227. So 20.227, and this is in kilowatts. So PI equals Q gamma E. So our E here is the head added. So 20.227 kilowatts, that is 0.03 for the Q. And since we're using kilowatt here, we are going to use kilonewton per cubic meter. So E is now equal to 20.227 divided by 0.03 times 9.81. So 68.73 meters. So that's the answer for letter C. So that's for sample number 4. Okay, so that's all for this lecture video.